Okay, so this is understanding of plasticity. Now damage initiation and evolution. So see, we have already seen O to A behavior, O to A, right? This behavior from here to here. So that is elastic behavior, and we can model it using only two properties: Young's modulus and Poisson's ratio. Then A to B behavior, this behavior is plasticity behavior or plastic behavior. And A to B behavior, we need Johnson-Cook plasticity model that will take care of strain, strain rate and temperature, and it will provide sigma bar value under this condition. Now the most important is when damage will initiate. So that is point B. Again, damage initiation in the machining process is again function of all strain, strain rate, temperature. I mean the strain at failure, this strain, this is the strain at damage initiation or failure initiation, epsilon naught. It is a function of your state of stress, how complex state of stress is. It is a function of what is the temperature, what is the strain rate, because machining involves all these harsh conditions. So again, Johnson-Cook also gave one damage model which will tell you at what strain damage will initiate in such a harsh condition. It is again function of sum of its parameter D1 to D5 and stress, state of stress sigma m by sigma bar. That ratio is called as stress triaxiality. So mean stress divided by sigma bar, equivalent stress. Sigma m denotes mean stress. Mean stress is basically hydrostatic stress, sigma 1 plus 2 plus 3 divided by 3. Sigma bar is basically 1 minus equivalent stress. Ratio of it, sigma m by sigma bar, we call it as a stress triaxiality. Then strain rate and then temperature. So all these three combined in one equation which will tell you what is the strain or equivalent strain at damage initiation. So this quantity will continuously evolve while the process. Once your strain or incremental strain cumulatively achieve the value of material property, this strain at damage initiation, then means this ratio will become 1. That time damage will initiate. Because your strain is continuously increasing. Once this strain is equal to strain at damage initiation, that is calculated using all these parameters D1, D2, D3, D4, D5. These are called damage initiation parameters. For a given material, these are available in literature. That is called as Johnson-Cook damage parameter. So once this omega will 1, your damage initiation will happen. Okay, we call it damage is initiated. But the story doesn't end here. After B, there is one more region shown here, declining region BCD. Sorry, BCF something. Okay, so that region B onwards, whatever is the region, we call it as a damage evolution. So damage evolution is essentially once damage initiates, material will get softened, its stiffness will degrade according to this law. It is stated here. Means if D is 0, your stiffness will be same as E. But if D is more than 0, let's say 0.5. So 1 minus 0.5 will be 0.5 times C. Means your stiffness is no more E, it is 0.5 times C. And this D will evolve from 0 to 1. So D equal to 0 means the point of damage initiation, that is point B. You can see here. I mentioned in diagram D equal to 0. And when D equal to 1, when damage is fully evolved, stiffness is fully degraded. So at point F, D is 1, so element will be deleted from the mesh and your chip formation process will continue. Means we started with zero loading, we move to A with elasticity, A to B plasticity, and then B damage initiation, and gradually B to F, that phase is damage evolution. At the end, your damage parameter D will take value 1, it will fully degrade the stiffness, and that degraded element will delete from the solution. In that way this process happens. Essential equations are noted here. How this D is calculated? So basically it is equivalent of displacement divided by equivalent displacement at failure, U bar F. This is material property. This is called as displacement at fracture. We can calculate from strain at fracture also. Fracture strain, you know, it is a material property. From that we can calculate displacement at fracture. Once this ratio will become 1, your element will be deleted. So it will start from D equal to 0 to 1. It will evolve as U bar is increasing. And this D value will go in this equation. So if D equal to 0, you can see your effective stress sigma tilde will be same as sigma bar. And if D is 1, 1 minus 1 0 means your flow stress will be 0, sigma bar will be 0, right? So for D equal to 1, sigma bar will be 0 means that point is a F. So in this way, one more way, one can go with using fracture energy also. So in Abaqus, you can either define displacement at failure or you can define fracture energy. So from fracture energy also one can calculate, internally software will calculate displacement at fracture, and then it will further calculate the damage evolution or D, like that. So the all phases from elasticity to plasticity, damage initiation and evolution will define your complete material behavior in machining. So if you see, for elasticity we need to define two material properties, modulus and Poisson's ratio. Plasticity, we need Johnson-Cook plasticity parameter. I will highlight A, B, C, this N, M. These are all Johnson-Cook plasticity parameter. So these are 5 parameters. So 2 elastic properties, 5 plastic parameters, so total 7, plus this D1, D2, D3, D4, D5. These 5 parameters, so these are again 7 plus 5, 12, plus displacement at failure, 11. So total 11 properties are needed just to define a complete material behavior for mechanical loading, plus some thermal properties like melting point, room temperature, and to take care all your heat distribution and temperature distribution, we may need conductivity, specific heat, thermal expansion, density. So basically I can say you more than 15-16 properties are needed for a given material. material for machining simulation. So one can imagine how this is a rigorous process as compared to your simple bending problem or your tension test problem.